Good evening, everyone. Geotechnical Engineering Chapter Part 8, Soil Mechanics Chapter 8, C page. So in this video, we are talking about a aquifer. In terms of, we do have two of them. The first one is a, a confined and unconfined one. The first, we're going to talk about the unconfined aquifer at the beginning. So we do have a well located at the center, and we want to pump out the water all the way down from the well. And then as you go farther from the well to the sides, you can see we have a two observation well, number one and number two, and this is our ground. This is our piezometric water table, and by unconfined, and that this is the permeable, impermeable soil beneath the aquifer. By unconfined, it means in the terms of thickness of our aquifer, which is H naught, there is no permeable or impermeable layer of soil located. So all height of H naught is just by one layer of soil. And then the ground piezometric water level, and at the very bottom of aquifer is impermeable soil or rock. Mhm. And then all the way through this part is a queue in. We do have a C page all at a the overall height of the total height of aquifer, and that's another meaning or referring to unconfined. It means all the height is freely available for water to move in and out. So if we, for example, if we just locate we call this distance to a well to the left, like distance of r, and this small distance is an elementary format like dr, and then we'll talk about the detail about these things. So, and again, this is a original piezometric surface of water, which is a somehow below the water level, ground level, and r naught is from the center line of the pumping well to all the way to we call that R naught or radius of influence, where we can uh, by reaching to that point there is no effect of this pump to the ground level or water table in that distance. We'll come back to that. So we want to reach to a steady state condition, SSS condition. Mhm. And from Darcy equation, we do know Q or discharge is K. That's a coefficient of permeability of the soil, or we call that in a more technical term, a hydraulic conductivity of soil, which is either in feet per seconds or meter per seconds, and it can also be on other units as well. So that's just the hydraulic conductivity times I, which is hydraulic gradient, and times the area of that section. So it means, like, if we have other dimension of this part, that would be our area. And that's exactly equal to Q of pump, discharge of pump, which is going out of the well. And as soon as you know, by the definition, hydraulic conductivity I is dH by definition. I is in terms of a slope, that's rise over run. In concept, that's a dH over dl. How much water get tired when travel a distance of length. That's dH head loss over length of distance traveled from, for example, A to B. And if we just want to show it on graphically, it just says dH is just rise and run is dr or dl. And to be completely accurate, a DL is the red part at the top here. Mhm. But if alpha is small enough, or less than and 10 degrees, we can simulate tangent sine of alpha is equal to tangent of alpha. So we can use dr in terms of simplification. So in that, by replacing in the Darcy equation, Q is K dH over dl times area, which is 2PRH. And my area is the area of my well. And then, as we talk about, if it's alpha less than 10 degrees, it's sine of alpha simulated by tangent of alpha, and we can replace dH over dl by dH over dr. And it just makes it far simpler for integration wise. And again, rearrange and jot down the Darcy equation again, and it just k dH over dr times 2 pi rh, and then rearrange it again. Dr over r is equal to a constant times h dh. Now, if you integrate our equation from both sides, it just gives you ln of r is equal to 2 pi times K, hydraulic conductivity, over discharge times a half of H squared. 2 cancel out by the 2, numerator and denominator, and then you can have it like for the 2 observation well, like Q or discharge is hydraulic conductivity in numerator times pi times H2 squared minus H1 squared over a ln of R2 minus over R1. That's how we can derivate the equation for an unconfined aquifer. We'll solve uh, a numeric example, which can be also applied in groundwater problems and also in soil mechanics. Like, if you pay attention, you can easily see, as soon as you're moving from the well to all the way to piezometric level, if you have it like first, second, and third one, you can see the slope of this line is just reducing and goes all the way to a zero slope. So that says I maximum locates at the location of the well. At the very beginning of the well, we have the maximum slope, and that's I maximum. And as soon as you travel to the first observation well and second observation well, as you travel all the way to the piezometric level of water table, you can easily see how a I or hydraulic conductivity is getting smaller and smaller and goes to zero at the uh, radius of influence. So one can say tangent of alpha, which is equal to I or hydraulic gradient, the slope of, one can say, the slope of the groundwater surface from the horizon, called hydraulic gradient, which will reduces by traveling farther from the center of the well. And as you can see, the maximum is at the very beginning of the pumping well, and it just going smaller and smaller, getting smaller and smaller, and all the way goes to zero at the water table in a distance of a radius of influence. We'll solve a numeric value to see how we can use this interesting concept in problem solving. Thank you. See you in next video.